let us start. So I will present to you today some results of the project Cora, quantum optimization with resilient algorithms, which is one of the projects of the Competence Center Quantum Computing Baden-Württemberg. And also, so I am Thomas Wellens from Fraunhofer IAF, and then later my colleague Vamshi Katakuri from Fraunhofer IAO will take over for the second half of the talk. Before I start, I want to raise or to discuss the question whether quantum computers are indeed useful for a solution of combinatorial optimization problems. So that's a quite big class, going from traveling salesman problem up to feature selection portfolio optimization. And if you think of the use cases for the quantum computing, there are some clear, well-known cases where it is really proven that quantum computing will be better than classical computers if sufficiently many error-free qubits are available, like, so for example, this factoring of large numbers or quantum simulation for quantum chemistry. But in the field of the combinatorial optimization, the situation is less clear. So there are algorithms, quantum algorithms, which are proposed to solve such problems like the QAOA, but it's not yet really known how this will behave for a large number of qubits. And there are hundreds of articles which you can read about QAOA, but there are not only a few of them really compare what is the outcome of the quantum algorithm or the performance compared to the best known classical methods to solve this problem. And here's one of the few exceptions who try to discuss this question. So here it is for a max-sat problem, and they look at the time needed to find the optimal solution, which on a classical computer scales exponentially, and then they have some results with QAOA on a simulator for a small number of qubits and try to extrapolate this to a larger number of qubits. So the message from this graph would be that there will be some quantum advantage, but only at a large number of qubits and computation times of the order of days, weeks. But I do not think that this is the final answer, and there's still a lot to be done. Later, I will come back to this graph and discuss why I am skeptical that this way of extrapolating here is correct, and also there might be also other algorithms or different implementations of the QAOA or other algorithms where this picture here might change. And this is now coming to our project Cora. This is one of the aims of the project to bring a bit more clarity into this question. And also an important focus is the role of the errors. So what can one do with computers that still have some finite errors? And we want to, in this project, we want to tackle this question on different layers. So the first layer is the error characterization, where we take the system which we use is the IBM computer in Eningen, and we characterize what type of errors occur there. And then methods to reduce or to mitigate the errors are also treated. And then algorithms which can still tolerate some amount of errors. This is the third field here. And then finally, we are also looking at possible applications. So in the previous talk, there was Gerhard Hellstern, who has already spoken about the feature selection. And then later, Vamshi will talk about the risk analysis. And now in my part of my talk, I will show some results mainly about error characterization and about optimization algorithms. And here are also the partners which also take part in this project, like so Fraunhofer IAF, IAO, then Universität Tübingen, Universität Konstanz, Universität Stuttgart, and DHBW. So now the first layer is the error characterization. So what we have, so here you can see the connectivity map of the Eningen device, and then one can each of the CNOT gates can be the error rate can be measured with randomized benchmarking, and IBM is also doing this every day, and they are providing the data. And this is here the red bars, and we have then to check this and also measured these rates. First, we measured all the CNOT gates individually, and then we get almost the same results. But it turns out that if one measures different CNOT gates at the same time, which have also neighboring qubits, then in some of the cases, then the error rate drastically increases, and this is a signature of the crosstalk effects. Yeah? And we were able to identify in some of the cases the physical origin of this effect. So, for example, here, if we apply a CNOT gate on 2225, then the microwave pulse is applied to the qubit 25 with the frequency of the qubit 22. And it then turns out that if the qubit 24 here happens to be in state 1, then the frequency of the transition of this system to the second excited state, which normally should not be occupied because we want to have qubits with only 2 states. But this frequency almost coincides with the frequency of qubit 22, and therefore this unwanted transition is excited in this case. Yeah. And a similar, more complicated effect here occurs with qubits 2, 3, and 5, where one qubit goes from 1 to 0, and another one goes from 0 to 1 to 2. And this can be understood with these frequency collisions. And we have then also set up a noise model which includes these effects. So one can use there is in Qiskit there's also a noise model from backend which is provided and which is supposed to mimic the real behavior of the backend. And what is taken as input there are the decoherence times, relaxation times, average error rates, which are measured every day. And then all these errors are then modeled as the thermal relaxation errors and depolarizing error. And this is the, so to say, the standard model. And we have then added there our measured data, including the crosstalk effects, which means, for example, if we apply here a CNOT gate on the qubits 0 and 1, and and the neighboring qubit 4, for example, happens to be active, which means that some operation has been done on this qubit before, then we should then take the higher error rate of the CNOT gate, including this crosstalk effect, and put this into the model. And also on the neighboring qubit, there's then also some effect with a corresponding error rate, which we have measured, and thereby we have then set up this model, including the crosstalk, and we then checked how well does this model agree with the real results obtained on the hardware. So here we have taken, as a test circuit, we have taken this one here, which is not important at the moment. So just for testing, and here this has 8 qubits, and if we execute this circuit on the 27 qubit system, the question is which of the 27 qubits should we choose for this purpose. So here are 2 possible choices are indicated here, and in total there are 132 possible choices, and we have then checked all of these different layouts and run this circuit on the real device and compared how close is the outcome which is measured to the ideal outcome which would be obtained without errors, which would be like this here. And then we have checked what is the outcome from our noise model compared to the outcome of the real device. But first we have taken the standard noise model, and here are all these 132 different layouts, and for each one there's a fidelity which we measured, and there's a corresponding fidelity which would be predicted by the noise model. And one can see here that there are quite a few cases here where the simulated outcome with noise model would be quite large, but the real outcome is smaller than that. And if we take our extended noise model, we have in total a better agreement, which is still not perfect. So we are still working on it to model the errors more precisely based on a Hamiltonian simulation where we take 3-level systems which interact with each other to describe these crosstalk effects more precisely. And then I come to the next topic where we look at algorithms. And here I want to mention briefly here a recent article where we looked at the warm start QAOA. So what is this? So the QAOA solves a so-called Kubo problem, which is a quadratic function of a binary variable. Zi here is either 0 or 1. And it turns out that this is a hard problem to solve and takes an exponential time to find the optimal solution. But the problem becomes easy if one relaxes this condition that it must be either 0 or 1, but if you admit also values in between, then it becomes easy to solve this problem. At least if the matrix F here is a positive semi-definite matrix, then it is easy. And if it is not, then there are some tricks to reformulate to make it positive. And then there's the idea of the warm start QAOA proposed by Egger, where the basic idea is to take this classically obtained solution of the relaxed problem and take this as an initial state for the optimization. So where each qubit is then put in a superposition state, and Z star is the probability to find it in 1, and thereby you are starting with the initial state which is already in some sense close to the optimum. And indeed one can then find that if I look at the quality of the solution here, so here for a portfolio optimization problem with 10 qubits, as a function of the QAOA depth, you can see that this warm start indeed is better than the standard QAOA. And we have then found that we can reproduce the same effect just by purely classical pre-processing, where we, so first we look at this solution of the relaxed problem, and then it turns out that some of the bits which are found there are already quite close to 0 or 1, and we just then fix these bits to the 0 or 1, and they are eliminated from the problem, and the rest then can be solved with a standard QAOA. And this method is here in this case it's even better than the warm start. And I think this is a nice example where one can take a problem and solve a certain part of it first classically, and another part then with a quantum algorithm. And I think there's still a lot to be explored in this field. And then I promised to come back here to this initial picture where I showed here the comparison of the classical time to find the optimal solution of this method problem with the QAOA. And I said that I'm a bit skeptical about whether this extrapolation is correct. And the reason is that they have considered here only a constant depth of the QAOA, which is here. So the red points are all for depth equals 4, and the green one for depth equals 8. And if you increase the number of variables, then what should be done is to also the depth must be increased to still find the optimal solution. And therefore I don't think that this here is correct, and we have then tried to find our own answer, and we then looked at the portfolio optimization, and we took then a number of qubits from 10 until 28, and we also focus now on the time to find the optimal solution. So first we take as a classical reference, we take an algorithm from the library MQLib, and we see how much time this needs to find the optimal solution. And to compare this now to the QAOA result, we so to say we try to estimate the time that would be needed to execute all this optimization on the quantum computer. This of course depends now on the gate time and the preparation readout time. And to make it a bit simpler, because we are only interested in the scaling behavior with increasing a number of bits, we concentrate on the depth of the circuit. So the deeper the circuit is, the more time it needs, and the more shots you execute, the longer it takes. And we just count the depth of every single circuit which is executed during the whole optimization. This is then our estimate how the time that would be needed on a quantum computer to solve this problem. And there we find so classically we find that as a function of the number of the variables, so we have 10 different instances for each number of variables, and there's a quite large spread that sometimes the solution is found faster than in other cases. But if one takes the median, that is a blue curve, and you fit it, the time roughly scales like 2 to the power of n divided by 3. Yeah? And here is now what we found with our implementation of the QAOA. So we have 1,000 shots per circuit, and therefore it's clear that if we have a small number of qubits, like 10 qubits, we have only 1,000 states which are there. So if we do 1,000 shots, we will, for this case, just by pure chance, we will probably already find the optimal solution. And therefore, at the beginning, so for small number of qubits, the time scales like exponentially 2 to the power of n, like a brute force search. And only later, the effect of the QAOA, so the optimization of the circuit parameters will set in, and it will then scale a bit better than the brute force, like 2 to the power of n divided by 2. But presently we do not yet see that it will outperform the classical algorithm. And we are still looking for maybe different implementations of the QAOA or different variants where maybe one can then find here a better behavior. Yeah? And also, it would also be useful also on the classical side. One needs to identify classical problems which are also difficult for the classical computer. Yeah. And then my colleague Vamshi will take over for the part of application risk analysis. Mm-hmm.
Thank you. Thank you, Thomas, for introducing the project and what it deals with. Right. So I'm going to talk about the algorithms which we could apply, the quantum algorithms for some of the financial applications, especially in options pricing. So the goal is to evaluation of the currently available quantum algorithms for options pricing. So options pricing, what it is, it's one of the ways we would want to invest our money with some risk associated with it. So as I've defined here, it gives the right to holder an obligation, but not an obligation, to buy or sell an asset at a later point of time, at a particular strike price. And the goal is to, what should be the price I should be putting in now? Yeah? And this can be described by this payoff function, that until the point K, where is the underlying asset value, you don't have any payoff, but once you cross that, you would have a payoff function which is linear. So this is something which we want to simulate and predict what would be the payoff for this particular option. So one of the radical models was developed by Black-Scholes and Merton. It's a model, BSM model, where they defined this whole process as a stochastic equation. Yeah? Meaning that you can generate many paths of the probable paths of the value of the underlying stock. And then you can solve this analytically solvable model to get the stock price at a point t in the future. Now, normally this is done using Monte Carlo sampling. It is not difficult, but it takes a lot of time and takes a lot of resources. So if you want to get a close enough result, meaning the number of samples you generate of this different price paths, the error decreases, or let's say the error is proportional to 1 over the square root of the number of samples. Yeah. So if you want to get an error which is less than 10 power minus 4, you need to generate 10 power 8 samples, yeah, of the price of this particular asset. And this is the simplest pricing, options pricing, for example, Europeans option. There are complex options, you have multiple options, combination of options, and so on. When this is not even enough, you need a lot more. So the promising thing about the quantum algorithms, one of them, if you can model your problem in such a way that you could use this amplitude estimation algorithm, which is quite intuitive here, I'll come into a bit. The benefit of this is that it scales not as a 1 over square root of k, but 1 over k. So 1 over the number of samples. So the error decreases faster. So the quantum amplitude estimation algorithm is that you encode the problem into your wave function psi with an additional qubit, ancillary qubit, with a 0 and 1, and you would want to estimate the amplitude of this 1. So root A. So if you can get this particular amplitude, you want to encode your variable into this such that you just want to estimate this amplitude, and then you can get the expectation value from there. So traditionally, the quantum amplitude estimation uses a quantum phase estimation, which I've put here, where it uses this state A with a combination of some rotation operators to actually estimate this amplitude, approximate amplitude A. One of the problems with this method is that it uses what is called as quantum phase estimation, which I show here, where the result is encoded in a set of qubits. Yeah? If this is your actual problem, qubits needed for your actual problem, you need some auxiliary number of qubits, a certain number, to actually hold the result. Yeah? And the resolution of this result, or the how fine you want this result, is encoded in this qubits. Yeah? The finer you want, the more accurate result you want, the more number of qubits you need to use here. Naturally, we know that the more qubits, the more noisy it becomes, and then your error increases. It becomes a difficult problem. So the idea is to see, are there approximates to these, at least in this formalism, and can we implement them on the current hardware which is available, and see where do we go from there. Okay, so here is the encoding of the problem. So in the amplitude estimation, we encode the probability distribution of our asset and the payoff function, this f of s, which is shown here, and the probability distribution. I took one of the probability distributions. It's a log normal probability distribution, which comes from this BSM model. And you encode this, and you use this traditional quantum phase estimation way of doing this, and I put the result here. So this is run on a simulator. So the blue one is the classical, which scales as a 1 over root of k. And this is the quantum version, which scales as 1 over k. The green line is 1 over k. So this is what we expect, and it works on a simulator. But as I said, we don't want to use this ancillary qubits. So what one could do is, you could do some classical post-processing instead of using the phase estimation to encode the result. So in that scenario, you only need to implement this q power k, which is the number of samples, the quantum samples, but not this ancillary qubits and estimation of phase through this Fourier transform, which I showed. So this way, I don't want to go into the detail of this classical post-processing, but you can implement it on the simulator, and you see that this actually still holds this 1/k, even though the post-processing we don't use the full quantum to encode the result. Now the question is, what happens if we take this algorithm and transpile it on the actual hardware? So I've used the IBM hardware here, and I put the operators which we implement. So encoding the problem of this, the options pricing, which is A, into this is the probability distribution, and this is the payoff function. To implement or transpiling this on the hardware, you see that you need 68 C0 gates. I put this 6 C0 gates because this is what defines this is the most error-prone 2-qubit gate. So this defines what we can do on our hardware. And one implementation of this operator Q, we actually need Q power K. One implementation of operator Q requires 234 qubits. This transpilation is one transpilation. So again, this transpilation is a problem in itself, and you could get, based on the condition of different qubits, each transpilation chooses different set of qubits. But remember that we need k times. K goes, if I go back to the previous slide, you see this is the k, 2 power 2 to so on. We at least need 2 to 3 points to figure out this scaling. So one implementation of Q itself, you need something like 234. So you could imagine that you have to run this Q multiple times. Yeah? So you would need a circuit depth which is quite large. So at least for now, I have shown a sample of this circuit diagram. This is truncated here. It's a lot more bigger. But the conclusion so far is the simplest case we cannot do on, at least on the IBM Eningen machine. Yeah? We should try it on a bigger machine. Or other ways is to model your problem not as an amplitude estimation, but in a different fashion. For example, you can model your options pricing problem as a Hamiltonian. And then you can run it as a time evolution or the imaginary time evolution of this Hamiltonian to get to the ground state. This is something which you want to do next. And this is the conclusion. And thank you for your attention. Questions? I would like to tell you that behind we have a demonstrator for this project. Deep dive, we can go in detail. You're welcome to come over there if you have additional questions or anything. Thank you.